So here's another example using the second principle of induction. So we want to show that every statement in propositional logic can be rewritten equivalently. Well, is logic not can be rewritten, is logically equivalent to a statement using only the connectors and not. Every statement in propositional logic is logically equivalent to a statement using only conjunction and negation. So, we got conjunction, disjunction, negation, implication, double implication, and there's more that are less commonly seen in math, but sometimes in computer science, there's the this thing that's the, what do they call that? The exclusive or. There's the nor, other things. But from just a purely complete standpoint of being logically complete, all you need is two connectors, just conjunction and negation. You could also do disjunction and negation. You could also do implication and negation. Okay, and the homework, I'm asking you to do the following. Do this same thing, just with implication and negation. So it's going to be a lot like this. Okay, very similar to this. All right, so proof. So base case. Um, so the proof is by induction on the number of connectors in the statement. Right? The proof is by induction on the number of connectors in a statement. Remember, there is always a last connector. Connectors are used in twos, right? They join two statements together, or just negate one statement, right? So there's always parentheses there. Sometimes we don't write them, right? Like A and B implies C is the same as A and B implies C because of operator precedence, to avoid cluttering up the statement, right? So for example, right, A and B implies C, like that. This is two connectors, and here is the last connector. Right there. This one, A and B implies C, is exactly the same. It's two connectors, and the last connector is the implication because of operator precedence. Right, but if you wrote it like this, like A and B implies C, this is two connectors, right? But now what's the last connector? What's the last connector?
The and.
The conjunction there, yeah. Right? Or like this, A and B and C and D. You don't know which one is the last connector. I mean, this is well defined, right? Because there doesn't need to be this association. But from a very strict construction point of view, you know, there has to be parentheses there. That's why we have that associativity thing. A and B and C is logically equivalent to A and B and C, right? Here, this is the last connector. Right here, and this is the last connector. Oops. I wrote the same thing. A and B and C. Here, this is the last connector. Okay, at any rate, there's always a last connector. Well, so this isn't the proof yet. I'm just explaining some stuff before we get to the proof. So the proof will be by induction on the number of connectors. Now, including zero connectors, the base case will be zero connectors. Actually, let me, not using only the connectors this and this, using no connectors other than. So let's say it this way, no connectors other than conjunction and negation. Including zero connectors. When you have zero connectors, well, you're not using any connectors other than and negation. In fact, you're not using any connectors at all. Okay, so suppose that, so just some statement Q. So I'm just going to write it as Q. It's not a bare proposition by itself. Suppose that Q has n connectors. Suppose that Q has n connectors. There's always a last connector. Right? Therefore, depending on the last connector, right, Q is equal to, not logically equivalent to, actually equal to, well, it could be that the last connector is conjunction. Or Q is equal to, could be that the last connector is disjunction. Or it could be that Q is equal to A implies B. The last connector is implication. Or it could be that Q is equal to A if and only if B. Last connector is logical equivalence. Or it could be that Q is equal to the negation of some other thing. All right. So in each of these five possibilities, how many connectors are showing?
Just one.
Just one. So how many connectors are not showing? Let's say n plus 1 connectors. So Q has n plus 1 connectors. Therefore, depending on the last connector, Q is equal to this, 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 or this. How many connectors are showing in each of these possibilities? Just one. How many connectors are left?
N.
N. Where are they?
All within A or A and B for the ones that have two.
Say again?
The N connectors?
Yeah, with the N connectors that are left over.
They're either in A or B.
Right, some of them in A, some of them in B. Where all of them are in A or in all, like in this one, all of them are in A because there is no B, right? Right. So if A has A connectors and B has, capital B has little b connectors, then A plus B is equal to what? So Q has n plus 1 connectors, and in all of these, okay, one connector is showing, the other n are hidden. Some of them are in A, some of them are in B. Okay, so if there's little a connectors in capital A and little b connectors hidden within capital B, a plus b is equal to n. In particular, how do a and n compare?
A equals n minus b.
Yeah, but how do they compare? Right? Yes, true. But how do they compare? Is I guess what I'm asking.
I don't
Bigger
think I
than,
understand the
less,
question.
bigger than, less than, bigger than or equal to, less than or equal
Oh,
to,
okay, yeah. A less than, equal to or less than n.
less than or equal to n. Right? And b and n compare how?
In the same fashion.
Same fashion. Hey, the stony silences from the rest of the crowd is getting to me.
I can start using different voices if you like.
Voice acting is cool, by the way. I love voice acting. Right,
I used to
so
do plays a lot when I was younger, and I kind of
Oh,
regret
okay,
not
huh.
doing them anymore.
Yeah. I watched a lot of Cartoon Network with my kids. So great appreciation for good voice acting. So suppose that Q has n plus 1 connectors. So Q is a statement. It's got a whole bunch of connectors inside of it. I'm not saying where they are. They're just in there. Okay? There's n plus 1 of them. We're just denoting it as a letter. So depending on what, and again, there's always a last connector. Like in all these statements here that, these examples that we did, like there's two connectors here, and this one's the last one. Two connectors here, this is the last one. Two connectors here, the conjunction is the last one. Here, conjunction is the last one. And then, in these two, this conjunction is the last, this conjunction is the last, even though these guys are logically equivalent, but there's always, strictly speaking, a last connector. So, depending on what the last connector is, Q is equal to, not logically equivalent to, Q is equal to A and B, A or B. A implies B, A if and only if B, or just A not. If the last connector is negation, implication, double implication, and or. So there's one connector showing out of n plus 1 connectors. So there's n left. Where are they? Well, some of them are inside A, some of them are inside B, or maybe they're all in A, or maybe they're all in B. We don't know. We don't know. So at any rate, what we can say is the following. If statement capital A has little a connectors inside of it, and statement capital B has little b connectors inside of it, then A plus B is equal to n. That's the n leftover connectors. And the upshot of that whole thing is that A is less than or equal to n, as B is less than or equal to n. Okay? So that's the idea. So again, for example, this statement here, P implies Q and R implies X implies Y and Z, like that. Okay, here the last connector. Okay, how many connectors? How many connectors?
5.
1, 2, 3, 4, 5 connectors. 5 connectors total. Right. Here's the last connector right here. Right. How many connectors do I have in this one?
Just the one?
One connector. How many connectors over here?
3?
3 connectors. All right. And 3 plus 1 equals 5? No, it equals 4. Here's the fifth guy. So we'll call that the fifth. That is the last connector. 3 plus 1 is equal to 4, and there's 5 connectors in total. We all on the same page? Okay. So, let's start with the proof. So let's look at that statement again. Copy it. So now we proceed with the proof of this statement. Show that every statement in propositional logic is logically equivalent to a statement using no connectors other than conjunction and negation. All right. So using induction on the number of connectors in the statement. The base case would be 0 connectors. So just a bare proposition by itself, right? The sun is shining. Just a bare proposition, the sun is shining. Connectors? None. So is that logically equivalent to a statement using connectors, no connectors other than and not?
It is.
Yes, of course. So a statement without any connectors at all uses no connectors other than and not. Okay, induction step. Okay, so the induction step is that, well, it's P0 and P1 and Pn implies Pn plus 1. That's the predicate logic notation for it, and it goes like this. So assume that any statement in propositional logic which uses k connectors, where k is from 0 to n, which uses k connectors, is logically equivalent to a statement using no connectors other than conjunction and negation. All right? So now that's the induction hypothesis right there. Unfortunately, we're out of time. Oops, where did it go? Yeah, unfortunately, we're out of time, so I guess we're gonna have to finish that on Monday. Um, Actually, I'll write up the rest of it and I'll post that online. Um, that way you can look at it over the weekend, and then we'll talk about it more on Monday. Okay, and then I'll have one more example using for the second principle of induction. Okay, so.